are separate. So we have some areas more dedicated to one thing and the other, but they are all working as networks. And because they are working as networks, we have to see how complex neurons work. And complex networks theory has been developed a lot in the last years, especially looking on social networks. So there's a study regarding social networks that has been developed, and they show you that, for instance, if you want to know someone through a social network, with 6 steps, it will be enough. So this means that if I want to contact Elon Musk, for sure I know someone that knows someone in 6 times, that knows someone that knows finally Elon Musk. So I can reach Elon Musk just with 6 steps. And this doesn't mean that we have a lot of connectivity, but that our network works like what we call small world network. And it's because we have these connections, but also we have some random connections that allow us to jump, right? And then we have the scale-free networks, which are networks with some nodes with high levels of connectivity, right? So let's say that a little bit our brain is placed here, thinking that we have high levels of modularity and kind of good randomness. So we have modular systems in which you can see that you have a lot of interconnections on these small world networks and some interconnection between them, right? So this is called also the Erdos-Rényi graphs, right? Anyway, what is important here is that the way that we are modeling the brain today is following large-scale networks, seeing that they work like small worlds locally and like hierarchical networks globally. And this comes also from the graph theory. So we are applying graph theory to our brain. See what we have like edges and nodes, the same as in an electric system. And we have also important connection hubs. Also, some parts named rich clubs, which have a lot of connections. I want to stress that our brain is not pure electrical. Some people think that, but this is not true, because only very early species had electric brains, but they have a lot of limitations. Indeed, our brains work with neurotransmitters, so that's why it's so important, as I said before, like dopamine and many other chemistry part of the brain. So it's really an electric chemistry brain, and there is no way that we can do something similar just using electricity. We will need very, very high sized thing. So this means that if we really want to go in deep with artificial intelligence, we need to think that electric computers has indeed a limit. So I'm just giving this point. We need to think of biological or bioelectric computers if we want to go on these, let's say, large-scale computers. I know it's not easy. And then the other thing, it's like what we do with the brains. We analyze them. We make a functional connectivity matrix and network by using voxels. Voxels are indeed pixels of 3D. You have to imagine that our brain, it's very much organized. Some people think that there's is like a mess of neurons and connections. It's not like this. It's very well organized with several layers and connections. So it comes finally with this kind of, let's say, of organizations. and analysis. Indeed, many works have been also developed, let's say, models through EEG's preprocessing and also coming with models. And well, I'm going to show also some of these models, for instance, the connectoma, right? So those models are how the brain is interconnected inside. You can see this is the result of 20 individuals interconnection of inside their brains. These are the two lobes. And you can see here, we have connector hubs with high density of connections. These are the number of synapses, and then we have provincial hubs, the mainstreams, let's say, with the number of synapses and so on. But now what it really thrills me is like not only we have the connectome, which is something that is a work ongoing with many different universities, but also how our brain we can define large scale networks. Yeah, we know that many people is working on neural networks, but in a very small scale, and our brain doesn't work like this. It works like large scale brain networks. And with this, we can define different kind of networks, like the default mode network, executive control network, silence network. I will talk about this now. Sensor motor network, auditory, visual, different kinds of visual, and the cerebellum, this automatic part. The default mode network, it's really exciting. It's the one you are, for instance, using when you are driving and thinking on something else. Yeah, you drive, think on something else. You arrive home, you don't know how you did arrived. You were just thinking on something else. So then the DMN, this default mode network, is activated, which is very dangerous, by the way, no? But it allows us to do two tasks at the same time, maybe not in good efficiency. Just to let you know, the people who practice meditation, it seems that they are able to disconnect the DMN. Yeah, this is also a research that today is still ongoing, but we can see these effects. And then we have the triple network model, which has been proposed by Professor Menon, and still today it's ongoing, right? So what he realizes is that you have the default mode network, but when you are trying to focus on some task, then the salience network, what do is to balance it and to connect the central executive network. So in that part, you are focused what you are doing. Maybe sometimes you switch again to the DMN. So, and this is the one place here in the insula who are controlling this switch between the two modes. That's really exciting also. The other thing is about emotions. So very recently this year, it has been published a paper in which shows that the different emotions, in that case, they select 6 emotions: anger, disgust, fear, happiness, sadness, and surprise. They work indeed in our brain like small world networks. And this is really exciting also to see how this brain really uses as, let's say, very similarly as social networks and many others. Then we talk about neurotransmitters. I think I will not have time. I don't know when I need to stop here. But we generate neurotransmitters when we have positive stress. So if we take a look on a very early paper, when we have low levels of stress, which is called hypostress, it's not creating anything. So we are bored, we are dissatisfied, we are frustrated. However, when we have some levels of stress, we have here an optimal activity in which we start to have productivity, creation, creativity, satisfaction. This is called eustress. However, if the level of stress is too big, which is very easy, you can see that very easy we go down, and we arrive to distress and burnout. So we can see people on these two areas, or bored down or burnout. So moderate levels of stress comes with neurotransmitters, and neurotransmitters are the ones who allow you good transmission of information between neurons. Because as I mentioned before, our brain is not pure electrical. We need neurotransmitters to create the communication. So this means we have the dopamine, one of them, which give you learning and motivation, noradrenaline also, that by the way, it also comes from the heart, which is giving you other state and attention. Another important thing is how our brain processes the information. I mentioned that we are looking at something, the visual nerve comes here, and then we have some part of pre-processing, what we call the dorsal pathway, which we locate where is the object, and the other, the ventral pathway. What we do is we process what is this object, and finally here in the prefrontal part we can understand it and take even decisions. So very close to the sensitive part, here in this part we have the motor cortex. So all these parts that we can move are disseminated here. Left side is in the right lobe, right side is on the left lobe, right? So we have the two parts of the body divided here and there. And yes, this is one part also that is really very important, especially for brain to computer applications, BCI interface applications. You can see applications in which you could use a band here to sense the electric activity here and control, for instance, a drone just with your brain. This is a normal experiment nowadays. There are many other things that we could talk, but I think that we are a little bit short on time. So we have also that our heart generates also hormones like amitriptyline, which control also the stress neurons, as we connect with said before, and oxytocin, which is also the one who, for instance, the woman who gave milk breast to the babies, they are also generating. Also love, trust, fidelity. I don't know, when you help someone, you generate oxytocin. When someone helps you, you generate oxytocin. When you see someone helping some other, you also generate oxytocin. So it's the hormone of the happiness, someone said. And we know also that the heart is very important, especially because we have also this communication with the thalamus, in which we can synchronize all the cortical activities. But however, if we don't have a coherence between the heart and the brain, having negative emotions like frustration, anxiety, worry, irritation, you can see that there's a non-periodic waves on the heart rate with a lot of harmonics. However, if we have positive emotions, you can see that the heart rate, it's almost sinusoidal. Yeah, heart rate is not a fixed value, as some people imagine. It's a value that is changing and it's changing because you have to maintain constant the blood pressure. Well, let's move now to the space. What we have in the space, it's microgrids in nanosatellites. So we have been developing a lot of research with a company called GomSpace, but now we are also doing many other things, especially what we call also CubeSat. So CubeSats are made on cube structures. And one of the exciting things in the space is that we get much more energy, around 20% if we look on the quantum efficiency of the spectra that we can get from there, because we don't have the atmosphere that is filtrating it. So it comes also with new technologies, like, for instance, triple junction or even 4 junctions, in which we have, you can see here, very high efficiency for a narrow bandwidth. So if we want to have larger bandwidth for the energy in the solar spectra, then we can stack a number of layers. So today we have 3 layers and even 4 layers for space applications. And now I can see that they are also coming back to the Earth. So triple junction solar cells are also common in terrestrial applications. And the other thing is that it's very important that out in space, even though this looks like a very familiar DC microgrid system, we have cosmic radiation. So solar panels have an efficiency loss. We have a study made together with Airbus company, and we will publish very soon about that, with exciting results, new results that we find out, like shooting protons and electrons to our solar panels. And of course, control systems are also in danger because of these cosmic radiations, because protons and electrons are shooting digital systems. Maybe the digital system will be hang up. This is called also latch-up effect, which happened to CMOS digital circuits. So this means that many times local controllers or primary level controllers are made with analog electronics. So it's really also exciting because analog electronics are coming to the space. And yeah, you can see here the efficiency on those solar cells, probably beyond 30% when you talk about 4 junctions, 4 layers, and lithium-ion batteries are already there, the same as you use on electric vehicles, we have on space applications. But it's very important to think that when we talk about geostationary application, we have eclipses very often. So we need to be sure that the system is designed to support the eclipse between, let's say, the sun and the satellite by the Earth. So many things has to be considered here, apart from the radiation environment and drastic levels of temperature. So there's a number of missions right now in the world with CubeSats. There's 3 unique CubeSats in Finland. So in which we had particle telescopes also and plasma breaks. And you can see also here, these are gallium arsenide 3-level solar cells with 42% of efficiency, and we have in every layer, each of these of the satellite, 4 layers, independent 4 MPPT chargers. So this is kind of the electric systems that you can have, like independent MPPT chargers, direct connection to the battery normally, in order to have the best efficiency here, and some loads which are sometimes connected through DC-DC converters, right? So especially when you have geostationary satellites, not so much for low Earth orbit, which also you may have this effect. But here what we have typically in a 15-year mission is a total equivalent fluence of 10 power 15 electron square centimeter. So this is a lot, and this of course impacts efficiency of the solar cells and probably battery systems. So we have been studying this, and it's really dropping down the efficiency. So we have to see what are the next, let's say, possible technologies for that. If we look on space stations, it's really exciting because we have the International Space Station, but also some others are coming, like Chinese with the Tiangong 1 and 2. And probably we'll have very soon companies also coming with private space stations. You can imagine who are they. So here the International Space Station has like 33,000 solar cells producing electricity for these lithium-ion batteries, which has been replaced. Recently, I think it was lead acid batteries. They have been replaced, and this is a full DC microgrid system. In the past was AC, but also has been replaced all by DC. So, and it's important to highlight that this is the primary power line and the secondary power system. So, primary is basically for generation and storage. These are the only bidirectional converters, and all the other is only one direction. Only one direction, which is the best in terms of efficiency. I'm saying this because some people think when you talk about microgrids that everything has to be bidirectional. And that's basically not true. So that's important to highlight this. And now it comes with the lunar base. So we know that right now lunar bases are coming with very exciting missions like Artemis, which is right now starting, and many others saying that they are going to have some moon promises from the past. JAXA with the Japanese, a lot of research, especially with hydrogen, and China as well. So where we are now? We are on the place in which NASA is planning to have this Artemis mission. The moon may be delayed till 2025. JAXA, the Japanese, as I mentioned, a lot of research on fuel cells, the hydrogen, I will talk about this now, and the Chinese. So we are right now with only robotic missions. The phase 1 will be the initial deployment and then expansion. But however, if we want to have extended and unlimited duration of stay, we need to solve some problems like what happened with the muscles, which right now we could not solve it. Site selection, where we have to put this lunar base. Well, it could be a non-polar region, however, they are not good because we have like sunlight and dark periods of 15 days each. So long for energy storage. So the best is to put it in a polar region, in which we have 6 months of uninterrupted sunlight and then 6 more months with frequent illumination and darkness periods. So we have 2 places in which is very like to have that. In the North Pole we have the Peary crater, in the South Pole we have the Shackleton crater. Shackleton crater has been studied by NASA for many years. You can see here in the red points the most illuminated areas. You have the Peary crater also here. You have also here the Shackleton crater with the equivalent 1 month illumination conditions. You can see here in the crown of the crater is the most probably place that you could have solar panels with towers of several hundreds of meters. How to supply us power generation system for this base can be electrostatic charge in the future, but is still under study. But as you can imagine, some people start to propose nuclear fission with microreactors. I don't think it's a good idea, you know. We have very bad experience here in the Earth. It's not necessary to reproduce experiences in space. While when you think about solar energy, it's really the best. Less mass, convenient, reliable, already test for space tech applications, having the best efficiency also in space, no radiation, environmental friendly. Yeah. What about the energy storage systems? It comes lithium-ion batteries, very strong, and regenerative fuel cells, because lithium-ion batteries, they have very good efficiency, we know, but they don't have very good high specific energy. This means that they are very heavy. So we need to have something like regenerative fuel cells to generate hydrogen from the electricity, and then when we eat electricity, come from hydrogen and produce electricity. So they are reversible, and they have been studied a lot for space. And for instance, in the case of JAXA, the Japanese are also pointing out this, and that's something very important here. The other thing is to look on the loads. So we have the crew habitats. I will come back with this. That's extremely important because we have to see the power that we need to generate that, especially oxygen, and to have for them an ecosystem. The other is laboratory and exploration. So basically rovers, electric vehicles, and so on. And then the in situ resource utilization. So how to use the minerals and rocks that we have in the moon and reduce the dependence with the Earth. So this is called also ISRU, and is the most energy and power demanded. So that means that these three things will be placed, and also communications will be important, because in the moon we'll have our own internet. It's called LunaNet. So LunaNet, it will come with also communication stations and with our own satellites. Sorry, we have also pressurized electric vehicles and unpressurized old-fashioned electric vehicles. So here, it's important that we focus on having a microgrid with the best, let's say, resiliency. It's to have a multi-microgrid system. So we think, for instance, according to our study, Shackleton crater, you could have a number of microgrids, of course DC microgrids, interconnected between them to support habitats, laboratory, charging stations, and ISR. Of course, we will need hierarchical control, the same that we have in our electric systems, in our brains. Reactive controllers, which are more like the cerebellum or primary control, secondary control with what we call the subsystem control, something similar as the limbic system or secondary control in electric systems, and the mission manager system, which is basically like energy management system, which is the tertiary control for the prefrontal cortex in our brain. We studied also transmission technologies, etc., and the different rovers, unpressurized, and the pressurized one. So that means that you have oxygen in the inside. But I want to finish my talk to show how we have been extended these ideas of microgrids also to create an ecosystem for space applications, together with the European Space Agency and the Autonomous University of Barcelona. in which I graduated as well with cognitive neuroscience. I collaborate with some of the people that has already this closed ecologic system, which is basically an ecosystem that doesn't have exchange with another environment. So it's kind of isolated. There are different examples, but none of them is like Melissa, because they are more focused on terraforming. And Melissa is more focused on create your ecosystem. It's a micro ecosystem in which we have the astronaut, which needs of water, oxygen, food, etc. And I have a trace of contaminants like heat, CO2, respiration, urine, solids, liquids, fecals, etc. We know that. It happens to us every day. And what do? We have an input, we have an output, and now we have to close the loop. And if we need to close the loop, we need to create an ecosystem. In this ecosystem, what we have is several compartments. The first one is to take all this waste into the bacteria. Those are thermophilic anaerobic bacteria. They create volatile fatty acids, mineral, and ammonia. And then we have compartment number 2 with the photoelectrophic system. Which we do is we remove the volatile fatty acids and we produce the food. This food can be given back to the astronauts. And now the minerals and the ammonium, it's given to the nitrification compartment, in which we convert ammonium into nitrate, and unfortunately we need some oxygen for that. Where this oxygen comes from, we have microalgae and we have higher plants from the photosynthetic compartment. In this compartment, we do the photosynthesis. So we remove the CO2 from our crew members and we generate oxygen for our crew members and as well for the nitrification compartment. We can eat, especially the higher plants, and we produce water as well. You can see that this is really a closed ecosystem, really exciting. And you can see here some pictures of the nitrification compartment. Here we have the photobioreactor with the microalgae here inside and the higher plants, which you can eat them. And then here our crew members today are rats. The calculations are 40 rats equivalent to 1 astronaut in terms of oxygen and also food and generate of waste, right? As we mentioned before, fecals, etc. Yeah, 40 rats, 1 astronaut. And then our system have hundreds of state variables. So it's really complex. Hundreds of state variables. And they are non-linear dynamics and interactions between them. When you try to stabilize something, something else is destabilized. So it's very complex. And we wanted to keep the oxygen to 21%. This is with this the photosynthetic compartment. And also at the same time to keep low levels of CO2. We came with the idea that how to control this should be something very similar as in an islanded microgrid. So indeed, if you look on the closed ecosystem, what we have is the photosynthesis, which is converting the photons to, let's say, kind of oxygen, right? So it's kind of similar as in photovoltaics, in which we convert photons to electrons. And then the electricity we store by means of energy storage, the same as we store the oxygen by means of oxygen storage tanks. And then we have microbial fuel cells, which works very similarly as hydrogen fuel cells. We think that they are two systems. One is biological, the other is electric, but they are isolated and they behave kind of the same. We could implement the multi-level hierarchical control system that we implement in microgrids and that we are using in our brains. Primary control, so this is for controlling the mass flow regulation between the elements. In an electric system, it's to control the power sharing and the voltage and current regulations. And in our brain is our cerebellum part, which is controlling all these automatic things. Then we go to the secondary control, in which in a microgrid is to restore the voltage and frequency deviations produced by the primary control. And in a limbic system, what we have is the emotional part. Here what we do is corrective actions, because this mass flow regulation also produces mismatches. And then the tertiary control, it can work like energy management system, which is in our brain, our prefrontal cortex, the one who's able to go into the future, make predictions, come back to the present moment, take decisions, decision maker. So kind of an energy management system. Here we have something similar. It's an optimizer for long-term optimal setting points of the whole closed ecosystem. And then at the top of this, we put a SCADA system, a supervisory control, and in the bottom we've put the control for each of the devices. Exciting. And we implement this developing also a digital twin from the pilot plant. We developed the 3 levels of control. Basically, we were using a lot MPC, model predictive control, for that. And you can see the results. Yeah, so you can see that every time we change the light intensity of this compartment, we change the oxygen generation, same as in photovoltaic systems. And then you can see the oxygen tank level is changing very similarly as the state of charge of a battery. We got very good results, which has been published in a number of papers. You can see here the oxygen is at 21%. We have ripples, same as you can have, for instance, in power electronics. Maybe different scale of time, of course, you can see here. And CO2, we keep below 3%, which is necessary for the life. I will skip a little bit those results. And I want to finalize my talk saying that yes, there is also another work that has been developed very recently, looking on how the astronauts, when they go to long-term space missions, the structure of the brain, the connectivity, the connectome that we mentioned before is changing also. So the results have shown also significant microstructural changes in several parts, especially in the sensorial parts, sensorial and motor, say sensory motor part. So we can see really a new generation of brains when it comes with human space exploration. Yeah, thank you very much for your attention. I hope that you like it. I put for you here some of our references about CubeSats that we have been published in the last 2 years, let's say. Solar cells for space applications, lunar base as well, and hierarchical control for space biosystems, biologic systems in these 1, 2, 3 papers, and also more focus on the high plan also development, especially for hierarchical control. Thank you very much. That was all. I hope that it was useful for you. And I want to finalize with this statement from Albert Einstein. He said we cannot solve our problems with the same level of thinking that we create them. Thank you very much.
Thank you very much, Professor Joseph. It was really very informative and timely topic, and really it's inspired me that how you relate the brain with the microgrids, and then the closed ecosystem with the microgrids, and the control systems of these systems. And it's really very informative. Thank you very much.
Thank you.
Uh, I have one question that uh, like how what do you think that neuroscience, like we have the neuroscience to overcome the microgrid problems, like uh, the control, protection, or maybe power quality issues related to that, how we relate this neuroscience with the microgrid problems? And the second question, what's mine, that what do you think that the future of the microgrids is? Like we have we got an idea that how we will be building the microgrids on the satellites and the lunar system or the Mars systems, but what do you think beyond this? Like how it will come in our real time life, like in on the Earth? Yeah, please.
Yeah. Yeah, thank you very much for the questions. They are really good. Regarding the how neuroscience will impact microgrids, it's going to be very much as we don't expect. Until now, we have applications using just very simple neural networks, but to understand that we have complex neural networks with different functionalities will come with another level of complexity. And indeed, we are working on protection systems, as you mentioned before. Protection is really something very complex, and and we are getting inspired on how the brain is solving this problem for that. So a number of applications will come with this. And then, if you think about our lives, yeah, I talk here about the space, and maybe you think, okay, whatever happened in space will not be reflected here. But I can tell you that a lot of the things that we will try in the space will be reflected back to the Earth. For instance, when you think about the space, it looks like it's almost mandatory a renewable energy system because you don't have combustion machines doesn't work there. So you need electric systems for sure. So everything is electric. You have robots, electric vehicles, chargers, solar systems. So it's really how to live a life much more electric, and then you can come back to the earth and see how this is impacting. And indeed, I can see a lot of, for instance, solar cells that has been developed before just for space applications like the triple junction that I mentioned that today is being used in the earth. So I think that it's very good that we invest on the space because it allows us to think out of the box. It enforces us to go into pure electric systems and to come back here to the earth and say, okay,
Question.
that's for instance oxygen limitations. It's something that when you think about the space, you even don't think about to produce oxygen to then burn it by using a combustion machine, right? So I think that this will impact absolutely the way that we do the things on the earth.
खाना है, बच्चे खा ले।
Thank you. I don't know if you have some other questions.
Thank you. Raheel have a question.
Um, Thank you, Professor. There's one question for you that what is the minimum criteria that should be fulfilled for peer-to-peer energy networks in microgrids?
what kind of criteria are you asking?
Yeah, what is the minimum criteria that should be fulfilled for peer-to-peer energy networks in the microgrids?
I don't see the. Do you mean the criteria in which sense? In sense of communication?
Criteria
In
for
sense
the
of,
peer-to-peer energy networks. Criteria for peer-to-peer energy networks.
the point. Yeah, I know what you mean. When you have microgrids connected to a distribution system, so it's basically a multi-microgrid system, and you want to establish peer-to-peer energy between them, what you will need is that the DSO allows you to make this kind of transactive energy. And this is possible if the DSO, that this criteria, if the DSO allows you to do that. But the other side is also that you will need to have the contracts to maintain the confidentiality between the owners. So then it comes with blockchain needs to have the peer-to-peer microgrids already going. Yeah. So basically, you have these two things to be needed. One is the DSOs allow this and allows this fully bidirectionality, and then the other is on the level of these contracts, smart contracts that has to be done through blockchain.
Thank you, Professor.
Yeah, thank you.
Thank you very much, uh, sir. Now we have a token of thanks for you. That thank you very much for your speech, and this is a sheet for you, the e-sheet, and, and thank you for your all the time you have spent with us. Even you are sick, and we can feel that your the throat is not well, and your voice sometimes like you struggle with your voice, but still you spend some time with us. Thank you very much.
Yeah, thank you, and I'm sorry if I was not clear all the time. Thanks.
No, it was okay. It was fine. Thank you.
Thank you so much, sir. I'm very delighted to present this token of appreciation for chairing this session to Dr. Raza. Thank you so much, sir. Hello.
Yes, sir. Assalamu alaikum. Sir. Okay, sir. I'm available here.
Now, I would like to introduce Dr. Raheel Muzammil, who is the session chair of the keynote speech from Dr. Francisco G. Longat. Dr. Raheel Muzammil is the first graduate of PhD in Electrical Engineering from the Department of Electrical Engineering, the University of Lahore. He is an academic researcher from University of Lahore. I would like to hand over the mic to Dr. Raheel Muzammil. Now the mic is all yours, sir.
Thank you. And this is the keynote session, and in this session, Professor Francisco Gonzalez Longat will present his small presentation on the topic of time simulation for ensuring secure future power system. He is the professor in Electrical Power Engineering at the Department of Electrical Engineering, IT and Cybernetics, University of Southeast Norway. His academic qualifications includes the PhD from the Venezuela, and he has also served in many universities of the UK, and among them, the University of Manchester and Coventry universities are notable. Uh, Also, he has been invited in many speeches in the universities like KTH Sweden, Belgium, TU Delft, Netherlands, and he has also authored many papers. Further, he is the chair of the Department of Electrical Engineering in many universities of like Venezuela, and he's also authored many books. Further, he has published more than 50 plus papers in IEEE notable research journals. Moreover, his research is supported by the Royal Society, British Council, UK India Education Research Initiative, and among the two most famous research projects are related to the smart grid and also to the smart multi-terminal DC microgrid. Now I'm going to invite Dr. Uh, Francisco Gonzalez Longat to present his keynote session. He's not available online, so we are going to play his video.
If you want about this, I highly suggest to visit the website fglongat.org. Well, but it's time to start this amazing presentation. And before I start, I usually present some motivation. What is the reason that I am talking about challenges and solutions for power converter dominated systems? And the best way that I found to introduce this kind of situation is basically using this very famous photo. I believe many of you know this photo. This photo is basically a photo taken in 1900s in United States of America. Specifically, we are talking about the Fifth Avenue, the famous Fifth Avenue in New York City. And this photo is basically taken on a Sunday, Easter Sunday in 1900. And as you can see, there are many people walking around, but also you can see that there are many vehicles on the road. And now probably you are wondering, where is the car? Because if you realize the majority of the vehicles here, they are basically horse carriage. But there is only one car in that very specific photo. But now
I would like to show this scene, but 1 years later. 13 years later, in 1913, this is again the same location. We are talking about the famous Fifth Avenue in New York City, in United States of America. And even is almost the same date. We are talking about the Sunday Easter on 1913. But now you are wondering, where is the horse carriage? And this photo is quite dramatic because you can see a massive change related to transportation in only 13 years, 13 years. And the reason here is that you can see how we move from one technology that is the horse carriage to a car that is basically moved by the internal combustion engine. And what is reality is that this new technology, internal combustion engines, they replace the horses. And it's very interesting because Henry Ford, this amazing businessman, American businessman, Henry Ford one time was asked about this radical change created by the internal combustion. And he said, if I had listened in the masses, all they wanted was a faster car. And to be honest, the 20th century has been dominated until a few years ago by the internal combustion engine, a technology that started around 1900s. Because if you look the technology, Henry Ford started the use of internal combustion engine in July 1903. And that was the starting point of this dramatic technology disruption. But probably you are seated over there thinking about why? What is the reason that this gentleman that's supposed to be talking about power converters is talking about a car, a horse carriage? And the reason is very simple, because now I can use the same photo, and I can ask you, in this case, where is the synchronous generator? And the situation is extremely simple. The situation is that we are changing the way that we are producing electricity, the way that we are consuming electricity, the way that we are transmitting the electricity. And this is basically a technological change that is right now happening in many countries around the world. And the question is, where is the synchronous generator? And the synchronous generator is a technology that has been for more than a century in electrical power system. But today, the behavior of those synchronous generators start to be challenged by a new technology that received the name power electronic converters. And you can see over there that there is a single synchronous generator in this amazing photo where majority of the technologies, the production and consumption, are using power electronic converters. But now, what is the agenda? The agenda for today is extremely simple. I will start with a short description about the path to net zero. We are moving to reduce the carbon emissions to reaching net zero, and even some countries, they are thinking about negative carbon emissions. But we will discuss a bit that later. Then we will talk about the paths that we need to do in this transition to net zero. And that discussion will be related with electrical power system because they have the most important or the key role inside the decarbonization of the energy sector. And then I will answer the question, what is the issue with power electronic converters? What is the problem related with the penetration of power electronic converters? Then I will discuss with you some of the possible solutions that we are developing right now regarding making an stable and secure power electronic dominated electrical system. Then I will go across a short overview about inverter-based resources, type of inverters, controllers, and so on, and some closing remarks, okay? Well, let's start this presentation. Let's start with this discussion, why we are moving to the net zero. And the reality is that the climate change is a full reality. You can see many evidence worldwide about the consequence of the CO2 emissions at the atmosphere. And right now, there is an immense pressure to reduce the CO2 emissions because right now we are in what we call a climate emergency. The glaciers are melting down, the ocean is increasing on height, and we are receiving the consequence of the global warming. Now, what is interesting is that many countries around the world, they have been committed in order to reduce these CO2 emissions. And there are many countries that they are already having targets in legal form that they engage for the net zero position. And in this slide, you can see that there are already several countries around the world that they are already in the net zero. That is the beautiful case. That is the beautiful case, for instance, of Suriname and Bhutan. Of course, those countries, they have many hydraulic resources, hydropower resources to produce electricity. But there are many other countries, especially in Europe, like Germany, Sweden, United Kingdom, France, that they are already committed and engaged in law to reach the net zero emission. For instance, Germany is already committed for 2045. Sweden 2025, and my favorite case, the United Kingdom, is committed to 2050. However, that is the legal document, but there are already places in the United Kingdom that they are already engaged to reach the net zero. Beautiful and large metropolitan cities like Glasgow, they are already committed for 2030. Manchester, the beautiful city, is committed to reach the net zero for 2038. And even in the south of England, Bristol is already committed for 2030. And of course, there are many other countries worldwide that they have committed, but they are basically in a proposed legislation. If you want to see more details about this, I highly suggest that you go here to this link at the bottom, and you can see the Energy and Climate Intelligence Unit. And over there, you can get more information about this tracker, about the work net zero tracker around the world, okay? But what is interesting is that many countries are committed, but there is already a path defined for reaching the net zero emission by 2050. If you go and look into this amazing document from the International Energy Agency, they define the path for net zero for 2050. The document that is titled A Roadmap for the Global Energy Sector is defining the path for the electricity and heat, the industry, the transport, the buildings, and other sectors in order to reach the net zero for 2050. And what is interesting for us is that, for instance, you can see here at the slide, by 2030, 1,020 gigawatts annual solar and wind power will be added to the generation mix. And what is very interesting is for 2035, overall net zero emission electricity will be reached for the most developed economies. And for 2040, the net zero emissions is supposed to be reached globally for the electricity sector. By 2050, we are expecting around 70% of the electricity generation coming from renewable resources like the solar photovoltaic or solar PV and wind power. If you want to read more about this, I highly suggest that you go to the website of the International Energy Agency and please read this very important report. But what is important for us is how can we reach that net zero? But also, what are the consequences? What are the main challenges coming from reaching that net zero for the electricity sector? And in this slide, I would like to show you the most important aspect that we need to take into consideration when we are talking about the electricity sector. What is interesting for us is that we are changing in many ways the electricity sector. For instance, production. We are moving from very large centralized power plants with a lot of inertia, but using a very no environmentally friendly technologies. We are decommissioning coal power plants, oil power plants, and we are expecting to decommission all those very old technologies that they pollute the environment and they don't contribute with the CO2 reduction. And instead of them, we are installing many small size renewable generation like the wind power and also the PV system. And what is important is that one element that is playing a very important role in this transition is the battery energy storage. Because as you must be aware, all those environmentally friendly technologies, they are highly variable because the primary energy resource. In the wind power, of course, the wind speed can change time to time. From the PV system, of course, we have the clouds and the PV power production can change. For that reason, battery energy storage is a key enabler in order to reach the 100% of renewables in the electrical power system, but at the same time, the net zero. On the other side, we have the customers. The customer has been for many years just a passive element inside the electricity sector. They have been consuming electricity and nothing more than that. They only pay for the electricity, for the kilowatts hour that they consume. However, that paradigm is changing. Right now, the customer is transforming the way that they are using the electricity. Right now, the customer is more active. They are participating in the system because right now, there are many customers that they has PV solar panel at the roof. As a consequence, they can have very distributed and highly variable but local generation. But at the same time, there are new technologies. There are new technologies coming to the market, like the electric vehicle, like the heat pumps, like the small size battery energy storage. And as a consequence, the customer is not again the same passive element inside the electrical power system. Right now, we have customers that they are producing electricity, and the legislation is allowing them to receive payment for that electricity. That means that the customer stopped to be passive component, and right now we use the name prosumer. Prosumer is a customer that has the possibility of selling electricity to the system. But if the customer is providing electricity to the electricity grid, of course the distribution system must change from that classical one-directional power flow from the top to the bottom. And right now we are having two-way power flows inside the distribution system. Right now we are using what we call the active distribution system because the distribution system is changing dynamically, and that is a huge change for the distribution system. At the transmission level also we are having many challenges, because those very large power lines going from very long distances, that they move bulk power, they are starting to be substitute for smaller power lines with a varied kind of topologies and interconnections. But what is most important is that the technologies of battery is enable the possibility that we install this battery energy storage at transmission level. We are talking about utility size battery energy storage. We are talking about several hundred megawatts and also for several hours. That means we are talking about huge battery energy storage. And of course, with the changes that we are having in production and consumption, the market is also changing. In the past, we used to have a very centralized market, a very national market, and in that market, we were dealing only about energy, kilowatts hour or megawatts hour. But the reason now is that if the customer is starting to produce electricity and we need to pay compensation to them and some tariff, of course, now we have more regional control. We have a market that is not only energy, and we are talking about decentralizing and ignoring boundaries in this power production, transmission, distribution, and consumption. What I'm telling you is that now the market is changing to allow a smaller generation unit to be part of these balancing services, to be active part in the production of electricity, and that is extremely exciting. Finally, to close this explanation, what I can relate to pass from the very time when we were only base operation, that we were extremely dependent on forecast and we react to the changes in the electrical power system. As renewable start to be a high component of the generation mix, we need to change the way that we are operating the system. Because right now, with very small generators, we have thousands of many or more of them inside the electrical power system. The decision taken cannot be a human-based process. For that reason, we are taking the advantages of the new technologies like machine learning, like artificial intelligence in order to take the decision. But also we are taking the advantages of the very fast computational power, and as a consequence, we are moving to real-time calculation, real-time decisions using distributed computing power across all the system. And also one very interesting point is that we are going further, because the classical operation was a situation of the main or the big market that was national, and then we react to the changes on the distribution level. But right now, we need to take into consideration and take the advantages that the prosumer can provide to us. Well, as you can see, there are many beautiful challenges. And I highly suggest, if you want to learn more about this, I highly suggest that you go to the Institute for Energy, Economic and Financial Analysis. This institute provides, in the case of Australia, some paths related to those changes related to the electricity sector. But now, why I am talking about power converter dominated systems? Because the reality is that as we are changing the way that we are producing electricity, and you can see over there that the future will be more renewable, like solar PV plants, large wind farms, and hydropower. Well, but also we will start to have very small distributed generation, solar PV at the roof of many houses, and also small and decentralized battery energy storage, some of them located at the demand side. But also some embedded technologies like the electric vehicles. At transmission level, of course, we will have utility storage. What I am trying to tell you is that now the way that the power system is created and is operated is changing. And if you look this beautiful slide, you will see that here we have power converter, over here, over here, over there, 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 there. And I can keep counting. Where is the sector? Because right now the situation is the amount of penetration of these technologies that they are using the power converter as interface. If you want to read more about the time, I guess that you go to my book, Modeling and Simulation of Power Electronic Converter Power Systems in Power. Okay? But any lie that I find, and it's just, but to be honest, this is not a dream. Depending on the country that you are located, the local reality is very different. And today, I would like to bring your attention to one of my favorite countries around the world, and that is Australia. In this slide, I am what is one of the most important reports coming from the Australian Energy Market Operator, AEMO. In March 2021, they published a report that is called the Engineering Framework. And in this engineering framework, this plot that you have in front of you appear. And what is interesting is that this plot shows the changes of half-hourly wind power generation and solar generation compared with the synchronous generator. What I'm telling you is that here you can see on the horizontal axis, I am presenting in gigawatts the IBR generation. IBR is the short name of inverter-based generation. I mean just power and in the per axis generation. And we are talking again about gigawatts. But what is important in this very interesting plot? That using three different codes, you can see year 2018, 2019, and 2020. And as you can see, they are very high penetration of solar and wind power. As you can see, the maximum level rise from 38% in 2018 to 47% in 2019. And what is surprising is in 2020, this level reached 52%. And 52% is a very important number because 52% of generation coming from power converters means that power converters were the majority of the technology used for power production. And what is relevant for me in this very specific presentation is that 52% penetration of power converters mean that the synchronous generator was a minority. And that is true because the synchronous generation decreased from 13.7 gigawatts in 2018 to 10.8 gigawatts in 2020. What I am trying to tell you is that Australia, at least, they are in the situation of a power converter dominated system. And that creates massive challenges. Massive challenges that right now I will discuss with all of you. Many of you are wondering, okay, we are disconnecting synchronous generator, we are installing so many power converter, but what is the problem? What is the issue with this massive power converter penetration? Well, as I presented in my previous slide, is happening in many parts the case of Australia, case of the case United States specific. Is that we are synchronous generators, we are increasing the number of power converters. For instance, I highlight here the of Australia. In 2020, 2% penetration, 40% penetration of synchronous generator and high 52% power converters. Now, moving this tendency, and you will see many countries more the penetration of power electronic converters. Probably you are sitting over there wondering, Professor, but it's possible that we reach 100% inverter-based resources. And that is the case, 100% of inverter-based resources. But what topic, this is not 100% power converter has been a reality in other systems. For instance, there are many micro sources, and also some chips that they are already using inverter-based resources. What I can tell you at the challenges is for Europe not there's still many good then appearing in short term in classical what I can tell is that new is funds country depending of the country that are located this or no. Now, what is well issue I love to use the interesting here. High power converters. And the issue is not because we are installing more power converters. The issue is related with the thing that they are extremely different to the synchronous machine. To be honest, a power converter is dramatically different to the beautiful classical synchronous machine. And the problem is that power engineers, we are confusing them. I present here two animals. I love those animals. On the left-hand side, you can see this four-leg animal. This is the Equus ferus caballus. That is Latin for horse. And on the right-hand side, you can see the Equus quagga. That is the Latin for zebra. Zebra and horses, they look similar. They have four legs, they have a tail, they have two ears, they have two eyes, they have a nose. They look similar. But this beautiful guy on the right-hand side, they have white and black stripes. And they look similar, but they behave extremely different. What I want that you take as a takeaway from this presentation is that the power converter is dramatically different to the synchronous machine. And what is the reason for that? Well, in this slide, you can see the two very interesting things. The synchronous machine is extremely simple. It's an electromechanical conversion device. It's an electromechanical conversion device. You apply mechanical power on one side, the shaft, and you get electricity on the other side. For that reason, receive the name of electromechanical conversion. And all the conversion is happening inside the rotating machine and basically using properties of electromagnetism. From the control point of view is very simple because you have at least two control loops, one for frequency and one for AC voltage, okay? It's extremely simple. But what is extremely important that all of you understand is that the synchronous machine has been for more than 100 years in the electrical power system providing services. Some of those services, even we power engineers, we complain about those services. For instance, short circuit currents. Short circuit currents few decades ago start to be a problem, and we were complaining about short circuit currents because the synchronous machine is able to be overloaded and produce high current, high fault currents. And that is an additional overcurrent that is possible because the machine has the possibility of dissipating this amount of energy. For instance, also, the synchronous machine have a rotating component that receives the name rotor. And this rotor have a beautiful electromechanical physical property that is called rotational inertia. And the rotational inertia is amazing and is helping us because provide the possibility that in a steady-state operation, during normal operation, and also during disturbances, they allow to minimize or to reduce the frequency deviation. And that has been a service that not much people noticed until a couple decades ago. Frequency control is extremely simple in the synchronous machine because the synchronous machine doesn't require so many sensors, digital processing signal, and so on. And also the system strength. Well, system strength is a very interesting concept that we have started to look at very carefully, probably 5 or 6 years ago. Because the synchronous machine always produces a beautiful sine wave that we can use inside the electrical power system. And we didn't consider the possibility that that signal start to be distorted and start to be also lacking of the sine wave shape. Well, what I want to tell you from this slide is that the synchronous machine has been providing services for many years. And because we are using dispatchable technologies as primary resources, to be honest, the control and the operation of the electrical power system has been extremely simple. But right now, I would like to tell you about the power converter. The power converter is not similar to the synchronous machine. It's delivering electrical power. Yes, it's delivering electrical power. But the way that this device works is extremely different. Because the power converter is using very small size semiconductor devices to do what we call commutation. And those very small semiconductor devices, they are extremely sensible. And that is the reason that when we think about the services coming from the synchronous machine, there are many services that we cannot provide with the power converter. Because the power converter has no overloading capacity. And if we include overloading capacity, that requires a lot of money. For that reason, the power converter is lacking of the possibility of providing the same services. On the other hand, the power converter has no energy storage capability. You can add energy storage like battery on the DC side, but it's not inside the converter. Inside the converter, what we have is ideal switches commutating and converting the electricity, no more than that. Another thing is that the power converter requires many control loops. It's very different to the synchronous machine, require measurements, require processing, in this case, digital processing. And the kind of controls that we require for those power converters, they must be extremely, extremely fast. What I can tell you is that from those power converters, we want to have many services, like services coming from synchronization and rotor angle stability. Frequency regulation is one of the services that we have been already using from power converters, and also voltage regulation. Many of the grid codes around the world, they are already including frequency regulation and voltage regulation. And also, if you look the IEEE 1547, you can see that this is a capability already asked for what we call the smart inverters. Damping oscillation is a possibility that can be enabled in these power converters. In fact, some of the grid code requirements in the UK already establish some requirement for damping oscillations. However, providing those services makes several challenges. Several challenges because, for instance, the capacity of those power converters is still increasing and depend basically on the size of these very small commutation devices. Also, the energy that is required must come from one primary energy resource, and that primary energy resource, of course, has many, many possibilities, but at the same time has so many restrictions. I will not go full details over here, but you must understand that the PV and also the wind power, they have restrictions regarding the situation of the primary energy resources changing. And there are many other limitations related with the inverter. For instance, if you are using the old technology that we call the grid following converter, the grid following converter requires a synchronization mechanism. And this synchronization mechanism is attached to what we call the phase lock. And the phase lock has been around for many decades. However, it's a technology that has some limitations. Also, there are limitations regarding the models because they are not a standardization at the moment. We are working in several working groups related to the IEEE, defining some of the main services and characteristics of those power converters, but there are many work to do, especially regarding the power system dynamic model. Right now, what we have is a manufacturer-dependent modeling, and also in the form of black box, okay? Well, but in order to move forward, we need to answer the question, okay, and what is the issue? Well, the issue is that we are losing the very beautiful properties coming from the synchronous generators, and we are having those very fragile components, the power converters. And well, in this sense, we need to define a new way to develop and to create the electrical power system. And it's time to discuss, okay, how can we develop a stable and secure power electronic dominated grid? And here in this slide that you will see in many of my presentations, I would like to show you the mechanism that we can follow in order to enhance the power system stability. And we can classify, or we can include the solutions into groups: the short-term solutions and the long-term solutions. The short-term solutions, there are many of them that we have been working for probably more than 1 decade. For instance, grid code connections. The grid code is the document created by many utilities and organizations around the world in order to define the minimum requirements, safety, and secure operations from the components that we are connecting. And many grid codes around the world have been evolved and have been adapting to this new power converter dominated situation. For instance, IEEE has created many standards, and this standard, for instance, the 1547, have evolved in the time. Starting in 2014, 2015, around those years, this standard have evolved until right now we have the smart inverter. The smart inverter is a power converter that now can provide functionalities to be friendly to the grid. And what I can tell you is that many other countries around the world, they already create or open the possibility of including more power converters in the grid code. For instance, in the UK, we are already defining the minimum characteristic of the grid forming converters inside the grid forming. Okay? In other countries, we have been using what we call auxiliary services. Auxiliary services, there are many kinds of services, but for instance, one of the most important services that has been starting to be more and more attractive as the penetration of power converter increase is the inertia. And for that reason, in some countries, they already start to ask frequency response, primary frequency response from the power converters. And more specifically, in some countries, they are already asking for the inertia response from power converters. And that is auxiliary services. In some other countries, we already define that we need to take some short-term solution. For instance, in the case of the UK, the short-circuit currents are decreasing quite fast. And one very simple way to produce short-circuit contribution is using what we call the synchronous condenser. The synchronous condenser is a synchronous machine that is working to deliver reactive power. But during a short circuit, they have the possibility of contributing with a short-circuit currents. And short-circuit currents are extremely important when we are talking about protections, specifically for overcurrent protection, detection, and location. And finally, some other countries, they are using what we call mitigation measures. And I will not go in details in this presentation because we are running out the time, but I would like to discuss some of the most important long-term solutions. Many countries around the world has been looking to enable primary frequency response in power converters. Primary frequency response can be enabled on them. However, what is very important that you must understand is that the power converter has not overloaded in capacity. It's not similar to the synchronous machine. For that reason, this synthetic inertia or digital inertia or emulated inertia, there are many names in the market, many flavors about this kind of, let's say, controller. Synthetic inertia has the limitation that require the value of that gain on that controller to be very careful specified. For that reason, the other possible solution for solving the problems related with power electronic dominated systems is, of course, using the converter. The converter, many people say that they are the problem. In opinion of me, I would like to say that the grid forming, the grid power converter is probably the solution that we are looking for. What we need to understand is that the power converter is extremely fast. They have the possibility to be even faster than the synchronous machine. And one of the paradigms that we are using recently to try to solve the problem of the, let's say, power electronic converters dominated system is using what we call the grid forming. The grid forming is a new control technique that basically is replicating the behavior of the synchronous machine. However, there are two very important characteristics that I would like to say regarding grid forming. The first one is that the model of the grid forming control can be in a circuit that is basically a voltage behind impedance. For that reason, this model is more replicating the behavior of that real synchronous machine. And second, because we are not using the classical synchronization mechanism based on PLL, this kind of synchronization is based on angle or based on power. As a consequence, these kind of converters with this kind of technology, they are more stable and they are adding more stability to the electrical power system. Well, we are reaching the end of this presentation, and it's really sad that we are running out of time, but it's time to make some conclusions here, and to be honest, some takeaway. And at this moment, there are many things that I would like to say, but I think the most important conclusion of this presentation is that you understand that the electrical power systems, they are changing. The electric industry is changing. And we need to change also the way that we are thinking, the way that we are developing, planning, and operating the electrical systems. Because now we are disconnecting many of those synchronous machines, and we are connecting more of those power converters. But in this photo, I would like to take this photo as the final message for this presentation. Because as you can see over here, I have a horse, but I am trying to put on them a costume that is looking like a zebra. And that is my main takeaway here, that probably we are trying to make the power converter to look like a synchronous machine. It's my opinion, my personal opinion, that we need to take the advantages offering these kind of power converters. If we are reaching penetration levels of 52%, like the case of Australia, why do we need to keep thinking and developing and operating the electrical power system when the center is not longer the synchronous machine? What I'm telling you is that probably we need to start to forget the synchronous machine paradigm and focus on developing, planning, and operating mechanism to take the advantages of those very fast and very beautiful power converters. Well, this is basically my message in this presentation, and this is the end of my presentation here, Power Converter Dominated System Challenges and Solutions. It was a pleasure having all of you and be here.
And thank you very much. This was the presentation, recorded presentation of Professor Dr. Francisco Longet, and he is from Exeter University, UK. And because of his flight issues, because he was flying from Europe back to UK, and he couldn't attend our session, so he shared with us this recorded video, and we just played here. And thank you, sir. You have a safe flight. And this is a token of appreciation for Professor Francisco Longet. And now we will move to the next session, and I hand over mic to the moderator, Ms. Marwa.
I'm very delighted to present the token of appreciation to Dr. Raheel Muzammil. Thank you. Unfortunately, the next keynote speaker, Dr. Muhammad Kamran, is not present, so we are skipping the third session of Day 2, Track 1. The conference will now take a break. Please assemble again to resume the conference after the break of Day 2. The break will continue to 1:30 p.m. according to the local time of Pakistan. Thank you.
Assalamualaikum and a very good morning, ladies and gentlemen.
Now I would like to invite Dr. Ali Raza, who is the conference general chair.
Warmly welcome you all at the opening ceremony.
खुदा करे मेरी अर्ज़ पाक पर उतरे.
I am Professor Dr. Mohammad Kamran.
The conference is being held by the Electrical Engineering Department.
We had 98 papers, out of which 7 have been accepted.
It is indeed a great privilege and honor.
This virtual event will connect researchers from around the world.
Keynote talks while track 2 comprises of paper presentation.
We'll be back with a sequel where the conference will be physical and will be held in